Hello and welcome to another Common Core Geometry lesson by eMathInstruction. My name is Kirk Weiler and today we'll be doing Unit 3, Lesson 3 on triangle congruence theorems. Alright, now this is an exceptionally important lesson because today we're going to see some criteria that will allow us to conclude that two triangles are congruent, i.e. they're exactly the same shape and size, without knowing that all the side lengths are the same and all the angles are the same. Strangely enough, we actually proved all of these theorems back in Unit 2. You may not have even realized it at the time, but we did by using rigid body motions. All right. Today, we're going to state the theorems. We're not going to prove them, but we're going to state them, but then we will use the theorems to prove other things, and we'll use them again and again and again. And we'll see more criteria as we move on to future lessons. So let's jump right into it. All right, there are three major ways that you prove that two triangles are congruent, and they all have nice little abbreviations and things like that, so let's talk about them. All right, one of them is called side angle side, and we're going to abbreviate it eventually, obviously, as SAS. Then there's angle side angle, we'll abbreviate that as ASA, and there's side side side, SSS. Now, what do each one of these things mean? Well, we'll see them and we'll take each one of them in turn. We'll explain what we mean by side angle side and angle side angle, etc. And let's do it. Let's jump into them and take a look at SAS. All right, side angle side. Let's take a look at the theorem. Two triangles are congruent if two sides and the included angle, that's a new piece of terminology, we'll take a look at that. Two triangles are congruent if two sides and the included angle of one are equal to two sides and the included angle of another. And again, equal or congruent either way. All right? So what do we mean by this? Well, let's say that we had this triangle. And we knew that it had a side length of 10 centimeters, a side length of 8 centimeters, and the angle in between was 125 degrees. And we had this other triangle that had exactly the same measurements. We would now know that these two triangles are congruent, that they're identical, okay? The included angle means the angle that's in between the two sides, Now again, think about how remarkable this is. This is enough to conclude that these two triangles are identical. We don't know what these two angles are, we don't know what that side length is, but we do know that they're identical to this triangle. Again, we proved this back with rigid body motions. Now, we will take this theorem as being something that we know, and we can now use it to prove other things. So let's jump in and use side angle side. Let's take a look at a proof that involves SAS. Exercise number 1. Use SAS to do the following simple triangle proof. Maybe simple should be in quotes. Given AB is congruent to CD and BD bisects angle ABC, prove that triangle ABD is congruent to triangle CBD. All right, we're going to do a lot of geometry proof in this course. Whenever you're getting ready to prove something, a couple different things. To begin with, start at the end. Make sure you understand what you're trying to prove. Now in this case, it's pretty simple. I'm trying to prove that the triangle on the top is identical to the triangle on the bottom. That's it. We could actually do this using rigid body motions with these givens, but we're not going to. We're going to use side angle side, and we'll see why in a second. In fact, we're going to almost diagram the proof right up front by doing what I call marking up the diagram. Let's take a look. All right, we're told that AB is congruent to CB, so I'm going to mark that. I'm going to put a dash through AB. I'm going to put a dash through BC. We're also told that BD bisects angle ABC. Well, what does that really mean? What it means is that this angle must be congruent to that angle. Put a little dash mark through them like that so I can tell the difference between them. So I know this side's congruent to this side and that angle's congruent to that angle. So that would be kind of SA. So how are we going to get SAS? Well, there is one side that remains that I know is congruent between the two triangles, and that's a shared side, a common side, and that's going to be side BD. I'll oftentimes mark it kind of like that, all right? And now you can already see the side angle side coming out. This side's congruent to this side, this angle's congruent to this angle, and this side is congruent to this side, all right? If we needed to, we could actually draw these two triangles separately to kind of lay that out. But honestly, we've sort of done the proof. Let me show you why, okay? Then you'll work on some of the other proofs on your own. So first things first, AB is congruent to CB. Notice how I put a little side there, okay? That's part of side angle side. It's not required, but it's nice. And BD bisects angle ABC. There we go, get my T table in there. Now, why do I know those two? I know these two things because, again, they were given. So how does the rest of the proof play out? Well, I can now say that angle ABD, which I marked, is congruent to angle CBD. Why is that, right? What reason would I put down? Well, I will put down an angle bisector divides an angle into two congruent angles. I'd like to take a moment, okay? If you're in a traditional geometry class right now with a teacher other than me, your teacher might say that it's completely acceptable to write down definition of angle bisector. And if they've said it's acceptable to do that, go ahead and do that. Early on, what I'm going to keep doing is I'm going to keep emphasizing what the definition of an angle bisector is, what the definition of a midpoint is, etc., etc. But you may occasionally see me put something down like definition of. So again, that's kind of up to your individual teacher. Some teachers actually want to see you write out the definition. But right now, we've got a side equal to a side and an angle equal to an angle. So where's that other side equal to side come from? That's that shared side. So I'm going to say, BD is congruent to BD. Do you remember the reason that we use whenever we say that something is congruent or equal to itself? Do you remember? It's called the reflexive property, right? I say the reflexive property of congruence. You can just say reflexive property. Some teachers might just say, write down the word reflexive. Who knows? Again, ask your teacher about that. Any of them are acceptable on kind of a standardized exam. Now take a look. What we've now established is that we have two triangles where we have a side equal to a side, an angle equal to an angle, and another side equal to side. Therefore, we can now say that the two triangles are congruent, and over here, we just say the Sas theorem. Likely, you'll just write down Sas, okay? The key is we have enough information now to conclude that these triangles are identical to one another. Simple, simple proof. That's all we're going to be doing today are simple proofs. But it's important to know if you can establish that you've got a side angle side situation between two triangles, that those two triangles are identical. Again, let me step back a little bit, pause the video now if you need to, and write down any of these statements and reasons, and then we'll move on. All right, let's do it. Let's take a look at another one of the theorems. All right, we had side angle side, and now we have angle side angle, which is almost the mirror image of side angle side. Let's take a look at what it says. Two triangles are congruent if a side and the adjacent angles of one are equal, respectively, to a side and the adjacent angles of the other. All right? So again, very, very similar to before. Let's take a look at an example diagram of where this would come up. Okay, if I've got these two triangles, I know that's 32, that's 32. I know that's 125, that's 125. And I know the length of the side in between them is equal. Then I can say that these two triangles are congruent. Notice again that the side has to come between the pair of congruent angles, right? It can't come over here. If I know that's 32, that's 125, and that thing's 10 and 10, the two triangles could be congruent, obviously. But we don't know that they are. In this situation, these two triangles have to be identical. They have to be. So just like with side angle side, we now want to do a simplistic proof using angle side angle. All right, exercise number 2. Use angle side angle to do this, quote, simple triangle proof. Given Q is the midpoint of Sn, and angle 1 is congruent to angle 2. All right. Now again, we're going to basically diagram how this proof is going to go before we ever put anything down on paper by marking up our givens. So let's do that. Q is the midpoint of Sn. What does that tell us? Well, be careful here. It tells us that SQ is equal to NQ. Why do I say be careful? I'm saying be careful because even though they look like they're the same length, even though they actually are the same length, I do not know that MQ is equal to RQ. I don't know that that segment length is the same as that segment length. And you want to be careful. I don't know that. So what else do I know? Well, they told me that angle 1 is congruent to angle 2. Those two angles are congruent. So I've got an angle and I've got a side equal to an angle and a side. The question is, where does that other angle come from? I need angle, side, angle, and specifically, the side has to come between the two angles. So that would be these two here. Is there some reason I would know that those two are congruent to each other or equal? Do you remember? Ah, they're a vertical angle pair. And we've established multiple times in multiple ways that vertical angles are congruent. And you can use that now. Even though it's not part of one of the formal givens, right? There's nothing up here that says they're a vertical angle pair. The plain fact is when two lines cross, angles that are across from each other are the same size. And there's our angle, side, angle. Angle equal to an angle, side equal to a side, angle equal to an angle. Let's do this. So, first things first, angle 1 is congruent to angle 2. Why? Because it's given. Now, we could have actually written that first given also right away. But as much as possible, I try not to do what are called given dumps. A lot of students will. That's taking all the givens and writing them in line 1 and then saying given. I like, personally, to put the givens into a proof where they make sense logically, and since I'm trying to do angle, side, angle, I just got the first angle pair congruent. Again, it's up to you. Now I'll put that second given in. Q is the midpoint of Sn. Why? Again, because it's given. Key, don't make a conclusion based on a given unless you've written the given down. But now, let's make a conclusion based on that given, right? What should you write down based on this given? Think about that and write it down. Can you do it? Well, we can write down that SQ, right, is equal to NQ. SQ is congruent to NQ, side. Now again, what do you write down for the reason? For me, right now, I want to write down the formal definition of a midpoint. In other words, a midpoint divides a segment into two congruent segments. If you just write down definition of a midpoint, is that okay? Sure it is, if your teacher says it's okay. All right? That's their sort of like decision from a classroom perspective. Again, on a standardized test, either saying the definition of a midpoint or actually writing the definition of the midpoint out is completely okay. All right, now what do we have? Angle equal to an angle, or congruent. Side congruent to a side. Now we want that final angle pair. Angle MQN, that's this guy, is congruent to angle NQS, or SQR. All right, and again, what should I put here? Vertical angles are congruent. Now, this is important, okay? That's pretty much what you have to write down here. You absolutely can't write down definition of vertical angles. The definition of vertical angles are two angles that are across from each other when two lines cross. That doesn't imply anything about them being equal. You have to formally state vertical angles are equal or vertical angles are congruent. But once you have it, then you've got everything. An angle congruent to an angle, a side congruent to a side, another angle congruent to another angle. So we can now say triangle SQR is congruent to triangle NQM by the ASA theorem, by the angle side angle theorem. All right? So simple enough. Again, let me back out of the way so you can take a look, write down any of the reasons you need to, and then we'll move on to our last theorem for the day, our last theorem for the day. Lots of theorems left in this course. Okay, let's move on. The final theorem is the side-side-side theorem. Let's take a look. Two triangles are congruent. Three sides of one are equal, respectively, to three sides of another. It really should say two triangles are congruent if three sides of one are equal, respectively, to three sides of another. All right. In other words, if I know that three sides of a triangle have the same lengths as three sides of another triangle, those two triangles must be identical. We saw this as early as Unit 1 when we were doing a construction. I can't remember exactly which lesson it was, but the title of it was Constructing Triangles Given Their Sides. If I give you the three side lengths of a triangle, every triangle with those three side lengths is identical. All right? That isn't true of shapes in general. If I gave you a rectangle that maybe had a length here of 5 and a length here of 8, we could easily have other quadrilaterals. Perhaps they would be a little bit bent, but we could have other quadrilaterals that aren't congruent that still have those side lengths. But a triangle, if you know all three sides, they're all identical, right? If those three sides are identical. So let's now do a proof with side, side, side. Okay, exercise number 3. In the following diagram, WY is a median drawn to side XZ, and WX is equal to WZ. Explain why triangle WYZ is congruent to triangle WYX. Use a paragraph proof. All right, so there's two main ways that you lay out geometric proof. One way is what we've seen with these, these T tables with a statement and a reason. And many students like these because they don't have to write a lot. They just have to get their statements down and their reasons down, and that's it. But it's also completely acceptable most of the time to simply write your reasoning out sort of as you think about it. Okay, and I'm going to show you how to do that here with a paragraph proof. And I'm going to try to split my proofs kind of evenly between paragraph proofs and T-table proofs. First, let's mark up the diagram a little bit. All right, we're told that WZ is a median drawn to XZ. Now remember what a median is. A median is a line segment that goes from a vertex to the midpoint of the opposite side. In other words, Y must be the midpoint of XZ, so this side must be congruent to that one. The next given's pretty easy. WX is just equal to WZ. So I'm going to put a double slash through that. WX is congruent to WZ. And what's the third side? Because that's a side equal to a side equal to a side. The third side is, again, a shared side. That will come up a lot, that WY is a shared side. So let's do it. Let's write out why these two triangles have to be congruent now. And it's not that hard, all right? So let's do it. Because WY is a median, Y is the midpoint of XZ, and XY is equal to ZY. All right? As well, we know WX equals WZ because it was given. Finally, WY must be equal to WY by the reflexive property. So, triangle WYZ must be congruent to triangle WYX by the side-side-side theorem. That's it, right? So a little bit different, and yet it has all the same elements that a t-table proof does. In other words, I'm making a statement, right? And then I'm explaining why that statement is true, either based on givens or based on the definition of something, right? Because WY is a median, we know point Y is the midpoint. Because of that, XY is equal to ZY. We know that WX is equal to WZ because we were told that. You know, it was just given to us. And finally, WY is equal to WY. Let's make sure that actually looks like a WY. By the reflexive property, it almost seems silly that we have to state that, but we do. You could even say, you know, these two triangles share side WY, so it's congruent to itself. Finally, we can say that the two triangles are congruent by the side-side-side theorem. All right. Again, let me step out of the way a little bit. Take some time now if you need to write any of this down, and then we'll move on. All right. Now, one of the things that you'll have to do with geometry proof is based on the givens, you'll have to be able to quickly figure out which of these three, and eventually there'll be more of them, sorry, but eventually there'll be more kind of these congruence theorems, but you'll have to decide which one of them you're going to use to prove the triangles are congruent. So our last few exercises in this lesson get at that idea. Which of the triangle congruence theorems should you use? So let's take a look at this next problem. Exercise number 4. In the following diagram, we know that BD is the perpendicular bisector of AC. Which of the three theorems would be used to show that triangle CDB is congruent to triangle ADB? Explain your choice. All right, awesome. So take a moment, use that one given, the fact that BD is the perpendicular bisector of AC, to think about which of the three theorems, SAS, ASA, or SSS, you would use to prove these triangles are congruent. And by these triangles, I mean that one and that one. Take a moment. All right, let's take a look. Well, let's mark up our diagram. We know that BD is the perpendicular bisector of AC. The fact that it's perpendicular tells me that this angle and this angle are right angles. The fact that it's a bisector tells me that AD is congruent to DC. That's all I get out of that given. That's all I was really told. But we have a shared side, which is this side. Now, if you don't see it yet, it never hurts to draw the two triangles separately. We have ADB, like this, and we have BDC, like this. And now to me, it's clear that we have a side angle side scenario. Side angle side, right? Why? Because AD is equal to CD. What is it? The angles that are equal. Well, angle ADB is congruent to angle CDB. Why? Well, that's because they're both right angles. And then BD is congruent to itself. And that's simply the reflexive property. We're almost doing a mini proof here. And really, why is AD equal to CD? That's because BD bisects AC. And really, isn't that more or less the proof? Right? We've got, our statements here and our reasons there. Okay? But it's easy enough, based on the information given, to tell that we would have to use side angle side. All right. Let's do one more of these. See if you can figure it out on your own. Exercise number 5. In the diagram below, we know that SU bisects angle RST, and angle RUT. Which of the three theorems would be used to show that triangle RSU is congruent to triangle TSU? All right, so I want to figure out which theorem I can use to prove that those two triangles are congruent. Mark up the diagram and see which one you think it is. All right, let's go through it. Now again, amazingly important. We're told that SU bisects RST and RUT. And it's important to understand that what an angle bisector does is it divides an angle into two congruent angles. It has nothing at all to do with length. Nothing to do with length. Angles aren't length, length aren't angles. That didn't make a lot of sense grammatically. It doesn't matter. Get back to this. If SU bisects RST, it means this angle and this angle are congruent to each other. And if SU bisects RUT, it means this angle is congruent to this angle, right? This pretty much means I have to be angle, side, angle because I've got two pairs of angles congruent to each other. Where does that side come from? It comes from the shared side, right? Right in between. And there it is, angle, side, angle. Easy enough. Now again, these are rather simplistic proofs, and hopefully we'll get into more complicated ones as we move on, but let's wrap up the lesson. Okay. As we all know, two triangles are congruent if all the sides of one are equal to all the sides of the other, and all the angles of one are equal to all the angles of another. And quite frankly, one way to prove that triangles are congruent is to show those sort of, if you will, 6 pieces of information. And yet we don't have to. That's the remarkable thing that we get out of today, which is that we can actually show that two triangles are congruent if we know only 3 of the pieces of information: side, side, angle, and side, side, side. And we're going to use all 3 of those. Those are going to be kind of our foundation to prove a few more sets of criteria, and then we'll use all of those to prove a lot more things in mathematics, specifically in geometry. But that's in future lessons. For now, I'd like to thank you for joining me for another Common Core Geometry lesson by eMathInstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.